So at the end of the last class, I was talking to a couple students, and they pointed out that there was some kind of rounding issue with the last two problems on the quiz that you took. So I'm going to go in and I'm going to regrade those quizzes by hand. I think the system, if you didn't have the exact value, I think the system rounded it up. If you put the exact value in, you got the wrong answer or something like that. But I'll go in, I'll make adjustments. So if you have credit coming, I'll take care of that probably Sunday. And somebody asked about a picture of the lab manual. I'll scan a copy of the lab manual front and back, put it up on a canvas so you'll have the ISBN number and you know exactly what it looks like. And then I promised another student that I'll put a link up for the software. If your lab manual doesn't come with a code or a CD with the software on it when you get it, then you can go to this website and you can download the software. You can actually get a trial version. I don't recommend doing that because I think with the trial version, I think you got some printing issues. You want to actually get the full-blown version. But I guess if you're really, really pressed, you can get the trial version. It might work for you the first week. But after that, you'll need the full-blown version. I think the software is between $35 and $45 or something like that. But I'll get all that information up. I'll make adjustments to the quiz. I'll put the link up for the software, and I'll make a copy of the lab manual, put it up on your canvas, and I'll do all that by or before Sunday. So what I want to do today is look at binary arithmetic, and not so much that you guys will be doing arithmetic when you work with the PLC, but we kind of, if you think about it, we're looking at what goes on inside the PLC, and so we just kind of want to know how the PLC handles numbers. So PLCs, as you know, as we mentioned before, can do calculations, and so pretty much anything a computer can do calculation-wise, a PLC can do. So we're just going to kind of take a peek inside of the CPU and then see how the PLC handles arithmetic. Before we get into that, though, I want to review a couple things. In the last class, we talked about converting numbers from decimal to binary and vice versa. And we talked about the fact that when the binary number, we have, I guess you would call it place value, but when we refer to it in digital systems, we call it weights. And so like in our base 10, this would be the ones place, and this would be the tens place, this would be the hundreds place, and this would be the thousands place. Well, in base 2, we mentioned that this would be the ones place, this is the twos place, and then in base 2 is that the pattern is it just doubles as you go from right to left. So this would be 4, this would be 8, and I go out to 16, 32, 64, 128. I can keep going. And so they call this 8421 code. And often what they'll do is they'll just make a box. They'll put this in like a little box like this. If you have 4 bits, a 4-bit number, just make 4 boxes. Put your weights in there. And then if I give you a binary number, now remember, when you write a binary number, I either have to express that as in binary, or if I write like a 1, 1, I leave it like that. I don't know if that's 11 in base 10 or a 1, 1 in base 2. So if you mean base 10, you'll subscript that with a 10. If you mean base 2, then that would be a 1, 1. But given that, I can just come over here and put a 1 here and a 1 there. I have a 2, I have a 1. So 1, 1, base 2 in our number system would be a 3. A 2 and a 1 is a 3. So by writing in this like little 8421 code, you can quickly convert a binary number to decimal and vice versa. So I wanted to review that. And then I kind of went through that last PowerPoint quickly. I think I started running out of time. But there's 2 things I want to just make sure you understand. One is the way we handle negative numbers in digital systems. There's 3 ways to do it. A sign bit, there's the ones complement, and then there's the twos complement. Now, with the sign bit, somebody asked the question, suppose I have this number. And I ask, all right, what's the most significant bit? Well, you got to know if we're using a sign bit or not. If we're not using a sign bit, then the most significant bit is that one. If we are using the sign bit, then this first number here becomes the sign bit, and then the next number there would be my most significant digit, my most significant bit. We don't really use a lot of sign bits though. That typically when processors work with negative numbers, they're going to use most often the 2's complement. So if I have a number, let's say I got the number, I'll just make something up. I got that number. If I want to take the 1's complement of it, all I got to do is flip the bits. Now remember, anything I'm showing you here on the board, we have to be able to do with digital systems. And what I mean by that is we have to be able to carry this out using and or not logic. And it turns out that this process is really all you have to do is not the bits. If you remember, we talked about not logic. Whatever's true on the input, the output is the reverse of it. And I'll kind of show you this later on, probably next week when we get to logic. But the point is, if I want to take the 1's complement of this, all I got to do is flip the bits. It's pretty easy. So the 1's complement of this would be every place I have a 1, I put a 0. Every place I have a 0, I write a 1. I flip the bits, and this is the 1's complement of this first number. This is kind of a digital negative number. A more useful complement, though, is the 2's complement. And to take the 2's complement, there's 2 ways to do it. If you go on YouTube, they'll probably tell you to take the 1's complement and add 1 to it. But a quicker way to do it, and an easier way to do it is, if I want to take the 2's complement, what I do is I write the number as it is up to and including the first 1. Write the number as it is up to and including the first 1. So in other words, from this first bit here all the way up to that first 1, I'll leave these alone. I just write them down as they are. This is a 1, 0, 0. And then I take the 1's complement of the next 2 bits. So that's a 0, I change that to a 1. That's a 1, I change it to a 0. So this is the 2's complement. That's another way to represent a negative number in a digital machine. So if you were actually designing digital systems, you'd have to know if your system is going to use A, a sign bit, B, the 1's complement, or C, the 2's complement. Then you would design around whichever one of those you're going to use. So pretty easy to do, nothing earth-shaking about that. Now what I want to do is I want to just practice some of these examples. And these examples I'm pulling right out of the PowerPoint. But what I want you to do is get a sheet of paper out, get a pen or a pencil out, and don't look at the PowerPoint. Don't cheat. Just what I want to do is we'll go over the rules. I'll put the same problems on the board that I have in the PowerPoint. And that's going to allow us to go through the PowerPoint like really fast. So we should be done with this lecture pretty quickly. So don't cheat. Just get a sheet of paper out. Don't look at the PowerPoint. And I'll put problems on the board. I want you to work it out by hand. We'll work it on the board. And then we'll go through the PowerPoint really quick because we would have done like 90% of the stuff on the board. So the first thing I want to look at is base 2 addition. We can do base 2 addition, subtraction, multiplication, and division. We can do division, but typically I don't do division. I mean, if you want to see how it's done, we can do it. But we're just in this lecture, we're going to talk about base 2 addition, subtraction, multiplication. Division is pretty easy. It's not a big deal, but I don't show it in the PowerPoint. So anything I've shown you here as far as these operations, we have to do this with and or not logic. And actually there's circuits that can do addition, a really simple logic circuit that can do addition. I won't go into that unless you want me to, but let's just kind of go through the rules. So really in any number system, a 0 plus a 0 is a 0. In any number system, a 1 plus a 0 is a 1. And in any number system, a 0 and a 1 is a 1. Now here, I have a 1. Now remember, this is base 2, so it's not a 1 and a 1 is a 2. It's a 1 and a 1 is a 0, and then I got to carry 1. This is called the carry bit. Excuse me. But you see, if I use my 8421 code, if I have a 1, 0, I got a 2, no 1s, so a 1, 0, base 2, in our number system is a 2. So a 1 and a 1 is a 1, 0. You don't call the 2, you call the 1, 0. So those are the rules for addition. They're pretty simple to do. The only thing you got to watch out for is when you have a carry bit. You know, you got to carry over to the next column, just like in regular addition. So here's what I want you to do. Again, do not look at the PowerPoint. And I'll put the problems on the board. I made a copy of the problems out of the PowerPoint. And just get a sheet of paper, and I want you to work these out. So we'll just do them one at a time. So I got, for this first one, I got a 1, 0, 1, and I have a 1, 0. And I'm not going to write the little 2 up here all the time. I'll do it for this one. But and remember this, so you can quickly convert these over. Nice to have this handy. So I got 8, 4, 2, 1. So I got a 1, 0, 1. I got a 1 here, so I got a 4 and a 1. A 1, 0, 1. I got a 4 and a 1. So this is a 5 in our number system. I have a 1 and a 0. We did that one already. I got a 1 and a 0, so that's a 2 in our number system. When I add these up, I should get a 7. So go ahead and apply the rules. Add these up and see if it actually works out. And if you're doing this, if you're actually doing this, I have a 1 and a 0. From the rule over here, a 1 and a 0 is a 1. A 0 and a 1 is a 1. I just bring down this 1. So I'll have a 1, 1, 1. That's a 4, a 2, and a 1. That's a 7. And so it works out. So go ahead and try the next problem, which I'll here put on the board, and see if you get the right answer. I mean, once you see how it's done, it's pretty simple. It's nothing, like I said, earth-shaking about this stuff. But it is interesting that you can do all this basically with gates, with just simple and or not logic. So now I have a 1, 0, 1, 0, and I want to add to that a 1, 1. Again, I won't write the 2, but we know we're dealing with base 2. So I like to convert these over. So I have an 8. So let me put it down here. This is an 8. I got a 1, 0, 1, 0. So I have an 8 and a 2. That's a 10. And that's a 3. I should get 13. So add those up in binary. Check it out, see if you actually get 13. I think that you find that you will. So go ahead and add that up on your paper. You guys gonna turn your cameras on. I can't really see if you're doing the work or not. My girlfriend teaches at not a public school, it's a charter school, and they do homeschooling, but they make all the students turn their cameras on. Make sure, because you can log on the camera and walk away from the computer. I don't know right now. You could be in the bed sleep, not even doing the work. I'll just see your icon. You can send me a text for attendance, and you might not even be there. So they make them turn. We can't make you guys turn your cameras on. I got a 0 on the 1. It's a 1. Now here you got to be careful. I got a 1 and a 1. That's this one. I got a 1 and a 1, so that's a 0, and then I carry that 1 over to the next column. So I got a 0 and a 1 is a 1. I got a 1 and a 1 is a 0. And then that 1 is carried over to the next column. And then I say I got a 1 and a 0. That's a 1. I got a 1 that I just bring down. So that's an 8. That's a 4. That's 12. And that's a 1. That's 13. It actually adds up. So those are, I think, all the examples I have in there. No, there's one more.
Is it going to be?
Say it again.
Is it going to be always 8, 4, 2, 1?
I can't hear you. Your mic's muffled. Say it again.
Can you hear me?
Yeah, I can hear you now a little better.
Is it always 8, 4, 2, 1?
Yeah. So let me go back over that. So remember when we talked about number systems, and this is important because on the exam, I'm going to make up a number system or ask you to make up a number system. So you got to know how this is done. So in any number system, what we said was like, let's just go to base 10. So base 10 number system, we said that this was, that's the ones place, that's the tens place, that's the hundreds, and that's the thousand place, right? Well, what we said was that if we count these positions here, we go 1, 2, 3, 4. But when you count in digital systems, we don't start counting with 1, we start counting with 0. So if we actually do that, if we count these spaces right here, this is the zeroth, 0 with a TH. This is the 0th place, this is the first place, this is the second place, and this is the third place in the number. And why do you want to do that? Because now what you can do is, this is a base 10 system. I can take the 10 raised to the power of that position, and that gives me the weight. So what that means is, instead of writing a 1 there, this is really 10 to the 0. And this would be 10 to the first, and this would be, the 100 would be 10 to the second, and then this is 10 to the third. So I can do this in the base 10 system. Well, it turns out I can do this in any number system. All I got to do to get the weight in any number system is just start with 0, counting with 0, and it'll be the base to the 0 power, base to the first, and so forth. So this would, in general, this would be b to the 0, this would be b to the first, this would be b to the second, and this would be b to the third. Well, if our base is base 2, then this would be 2 to the 0, this would be 2 to the first, this would be 2 to the second, this would be 2 to the third, and that's where that comes from. This is a 1, that's a 2, that's a 4, and that's an 8. But with binary, it's pretty easy, because as you go to the left, the numbers just double. So that's a 2, that's a 4, double that, I get 8. Next one would be a 16. You know, if I get, on the example, if I give you a bigger number, it's easy, just extend this, just keep doubling this. 16, 32, 64, just keep doubling that. So yeah, it's always 8421. I usually, when I'm showing examples in class, I just use 4 bits because it's quicker. Now, what I was saying about the exam, what on the exam, let's say I give you, I don't know, a base, let's do a base 3 number system. I'll just make it up. I don't even know if there is a base 3 number system, but we can make one up following the same rules. So what would that look like? Well, a base 3 number system, I don't even know why I'm going over the exam with you. I shouldn't even tell you this, but I guess since you asked. So let's say I had a base 3 number system, 3 to the n. We said the base tells you the number of symbols. So in the base 3 number system, this tells you the number of symbols in the number system. If I take the base minus 1, it's the value of the highest symbol. So you say, all right, I got three numbers in the base 3 number system. If I take 3 minus 1, the highest number in that number system, the highest symbol will be a 2. So I can use the numbers, or the symbols. I can use a 0, I can use a 1, I can use a 2 in the base 3 number system. But the important thing is, it kind of relates to your question, how would the place values look? Well, all I would do is, this would be the base to the 0 power, this would be the base to the first power, this would be the base to the second power. So if I had a base 3 number system, the weights would look like this. This would be a 1, this would be a 3, this would be a 9, and that would be my place value. And so I can come in here on the exam, I can say, all right, let's say you have 1 of those, you don't have any of those, that you got 2 of those. What would that be in decimal? You say, all right, I got a 9, I don't have any 3s, I got 2 of these, so I got a 2, that's an 11. So it looks like, somebody say something? I don't want to confuse you guys, but yeah, so the answer to the question is yes. But I was just kind of letting you know that this is kind of cool because it works for a base 2 number system, but it actually works for any number system. And on the exam or quiz or somewhere, I asked you to do something with this. So I don't know if somebody's mic is unmuted or if you're asking a question. It looks like Nugent.
Yeah, I'm just looking at it.
Okay. Because I can see your mic is unmuted, but yeah. So I don't want to. I'll stay focused, but after the class, if you want me to go back into that, I can.
Thank you.
That's probably more than you asked for, right? Okay, we got one more example to do for addition, and then I want to move on to subtraction. So again, don't look at the PowerPoint. Just go ahead and do this to make sure you're doing it the right way. We got a 1. Got that. Then we got that. We're adding those. So if you convert this over, that turns out to be a 26 base 10. This turns out to be a 12 base 10. And this is a 38 base 10. So the question is, when I add these in binary, do we get the same thing? And I think you'll find that we will. So if I add these up, a 0 and a 0, of course that's a 0. A 1 and a 0, that's a 1. A 0 and a 1 is still a 1. Now I got to use this rule again. A 1 and a 1 is a 0, and this 1 over here is a carry. So 1 and a 1 is a 0, carry 1. And a 1 and a 1 is a 0, and I just bring down the carry. So a 1, 0, 0, 1, 1, 0 base 2 in our number system is a 38. If you type it in your cell phone and save the number 38, what you're saving in the device is not a 3 and an 8. What you're saving in the device is a 1, 0, 0, 1, 1, 0. That's how numbers are stored. Now, well, we really didn't say much about codes. I think I talked about that on Friday. But the difference between a number and a code is numbers always have place values or weight. Codes don't necessarily have a weight or place value. Sometimes, depending on the code we're talking about, it can use weights, or codes can just use a sequence of bits to represent data in different ways. We'll get into that on Friday. Okay, so anybody have any questions over addition? Addition is pretty simple. I think
How do you get 38 with that number? With that code? How do you get 38 with that code?
We got 1, 2, 3, 4, 5, 6 bits. So well, let me just do 6 lines. It'll be easier. We got 1, 2, 3, 4, 5, 6. So this would be 1, 2, 4, 8, 16, 32. We got one of these. So write this number here. I got a 1, 0, 0, 1, 1, 0. So I got one of those. That's a 32. Right? I got 32. I got a 36. And then 6 and 2 is 8. So I got a 32. I got a 4. That's a 36. And 36 and 2 is 38. So I just extended the 8421 code. So as I was saying, as you go from right to left, you just keep doubling these numbers so you can get your weights. On the exam, I might give you one with, I probably wouldn't do this, but I can give you a 16-bit number. You got to be able to take this out to 16 bits, but you'll have your calculator.
Professor.
But you see how that works?
Yeah, I just thought you just like repeat that code to like 1, 2, 4, 8, 2, 1, 2, 4, 8, 1, 2. Like I thought you went and repeat. Never mind, I understood.
Okay. Your mics are muffled. I don't know. Sometimes you come in clear. I'm looking at the computer. I should look at your camera. But I don't know if you're too close to it. But sometimes it's clear. Sometimes you're hard to understand. So, but I think you said you got it. So.
Yeah, I got it.
Anybody else? Questions, comments?
Professor.
Yep.
Why does it become 38 base 10 at the end?
This right here?
Yeah.
So I'm converting this binary number to decimal, right? So I just used basically an extension of the 8421 code. So I did the same thing when we had on the example. We had let's do this number we did in the example problem. So in binary, the weights are 1, 2, 4, and 8 if I have 4 bits, right? So what if I gave you this number, 1100 base 2? What is that in decimal? Well, what you do is you say, I got an 8, I got a 4, I don't have any 2s, I don't have any 1s. If I add these up, I get a 12. So 1100 in base 2 in binary in our number system is a 12.
Okay.
So yeah, so the point is that we do addition like, we do addition like, we can add numbers, but all of that addition is done in binary addition. Your processor is doing exactly what we're doing by hand. And actually, as I mentioned in the PowerPoint, all the operations are done using addition. I'll get to that later. I don't want to get too sidetracked. So yeah. So hopefully that's clear now. Everybody all right with this? You see what I'm doing?
Yes, thank you.
Okay. Yeah, guys, don't let me go on if something's not clear. Please stop me and ask me, because I can't see your faces like when we're face to face. I don't know if people are getting it or not. I assume you're getting it, but since I can't see your face, I don't know. All right, so let's move on to subtraction. The rules for subtraction. I want to put them in the same order that I have them on the sheet. So this is a 0, 0, minus. This is a 1, 1, minus. This is a 1, 0, minus. This is a, let me just stop there for a second. So in any number system, not just base 2, of course, a 0 minus a 0 is a 0. And a 1 take away 1 is a 0. A 1 minus a 0 is a 1. But what I want to do is this. I want to do 2 minus 1. 2 minus 1 is a 1. Well, how do I write a 2 in base 2? How do I write a 2 in binary? 1, 2, 4, 8. A 2 would be a 1 and a 0. So a 2 base 10 in binary is a 1 base 2. So I want to do 2. So I got to do 1, 0 base 2 minus 1 base 2. So that would look like this. I got 1, 0. That's not a 10, that's a 1, 0 minus a 1 gives me a 1. So a 1, 0 minus a 1 is a 1. Now, let me review something with you. Let's say I have, I don't know, I got 4, I got 2, and I got a 3, and I want to subtract from that 15. So I want to do that subtraction. Well, here's what you would do. Now, these are base 10 numbers. So in base 10, in our number system, if I want to subtract this, then what I got to do is I say, all right, I want to take 5 from 3. Well, I can't do that. I can't take 5 from 3. So since you can't take 5 from 3, what you do is you say, all right, I'm going to borrow 1 from here. Now remember, this is the ones place, and this is the tens place. So when I borrow 1 from the tens place, it comes over to the ones place as a 10. So you say, all right, I'm going to borrow 1 from here. You cross that out. You change that to 1. But the 1 that you borrowed comes over here, and that's really a 13. So you say, I got 13 minus 5, and that we can do. We do exactly the same thing when we deal with base 2. If I have a number, and I have a situation like this where the number I want to subtract from is bigger than the number I want to take it away from, I got to borrow 1 from the leftmost column. So I'll show you that here in just a second. So again, get your paper out. Don't look at the PowerPoint, and I'll put this first one on the board and see if you can do it. So I got a 1, 1. I got a 0, 1, base 2. What's a 1-1? What is that in decimal? Put this over here so you can cheat. What's a 1-1? A 1-1 would be a what? 1-1 would be a 2 and a 1, which is a 3, and a 0-1 is just a 1. So 3 minus 1 in our number system's 2 is 2. You want to do the same thing over here using those rules. So go ahead and see what you got. And using these rules is pretty simple. This first one is this rule. And the second one is that rule. So I got a 1 minus a 1, 0. I got a 1 minus a 0, so 1. And this is base 2. So binary 3 minus a binary 1 is a binary 2. It checks out. So that's the kind of thing you got to be able to do. Okay, so I don't know if you got it or not, but if you think that you got it, I'll be quiet and I want you to do this next one. Do 1, 1. And again, these are all base 2 numbers. I won't write the little 2. You can write it down there on your paper. So apply the rule to that, see what you get. We just did this, didn't we? That was a 3, and this was a 2, so that should give us a 1 if you apply those rules. So apply the rules, see what you got. And the way you think about it is this rule right here, a 1 take away 0 is a 1, so 1 minus 0 is a 1. 1 minus a 1 is a 0. So binary 3 as a binary 2 gives me a binary 1. Works the same way in decimal. All right. Now, I'm going to give you 2 where you have to borrow. So this next one you got to borrow. Then I'm going to give you another one where you have to borrow. If you get this one, then the other one's going to be a little bit bigger number to see if you understand how to borrow. So here's the problem. I have a 1, 0, 1 in binary. Now I want to subtract from that that right there in our number system is a 5. And this in base 10 is a 3. And so I subtract and I should get a 2. So go ahead and apply the rules to that and see if you actually come up with a 2 in binary. Now this is the one where you got to borrow because you can't take a 1 from a 0. So I got to get 1 from over here. So I'll give you just a couple seconds and then we'll think out loud and I'll give you one more where I'll just let you work through it all the way on your own. Give you about 15 more seconds. All right, that's 15 seconds. So, just thinking out again, I got a 1 minus a 1, well that's a 0. I got a 0 take away 1, I can't do that. So I got to come over here and borrow 1, so I cross this out, make that a 0. And the 1 that I borrow comes over as a 2. So that's a 1, 0. A 1, 0 minus 1, 1, 0 minus 1, well, of course, that is a 1. And a 0 minus a 0 is a 0. So in base 2, that's a 2. So it works out. So again, you borrow in binary exactly the same way you borrow in base 10. It's done the same way in any number system. Friday, we'll talk about 2 more number systems. We'll talk about base, octal, base 8, and we'll talk about base 16, which is called hex or hexadecimal. Done all the same way, exactly the same way. So let me give you one more of these that's not in this section, on the arithmetic section. And let's see if you come up with the right answer. So for this next one, I want you to subtract these two numbers. I got a 1, 1, 0, 0. And I got a 1, 0, 1, 1. Subtract those. So if you think you got this borrowing ideal down, see what you come up with. I'll give you a few seconds to work on that. All right. So, well, this is interesting, right? Because I got a 1. I want to take a 1 from 0. I can't do it. But I can't borrow anything from over here because that's a 0. So what you do is go all the way over to that third column. And I'm going to borrow 1 from here, right? So I'll borrow this 1. So I'm going to borrow this 1, reduce that to a 0. And that 1's going to come over as a 1, 0. So now I have this again. So now I'm going to borrow 1 from a 1, 0. If I borrow 1 from a 2, I still have a 1 left. So I'm going to borrow 1 from here. So instead of a 1, 0, it goes back to a 1. And then that 1's going to come over as a 1, 0. So now I'm using this rule. 1, 0 minus 1 is a 1. 1 minus a 1 is a 0. 0 minus a 0 is a 0. 1 minus a 1 is a 0. So here I had to borrow twice. I borrowed 1 from here. It came over as a 1, 0. Then I borrow 1 from a 1, 0. That's really a 2. If I take 1 away from 2, I still got 1 left. But the one I borrow comes over as a 1, 0. And then I'm using this rule. So follow that, try to follow the logic of this. Now, there's another way to do this I want to show you that's way easier. Let me show you the other way. It works kind of like this. If I want to subtract 3 from 7, so I say 7 minus 3, I'm going to get 4 in our number system, base 10. But what I can also do is this. I can take 7, and I can do the subtraction in terms of addition if I add the negative. I get the same answer. I can do a process of subtraction by adding the negative. Well, one way to write a negative number in binary is the 2's complement. So I can do exactly the same thing. I can get the number, the original number, which is the top one, and I can take the negative of the bottom number, which is the 2's complement, and I can add them, and we should get the same thing. So let's see if that works. I start with the original number, which is 1, 1, 0, 0. Now I want to take the 2's complement of this number. So the 2's complement, I got a 1, 0, 1, 1. The way you take the 2's complement is up to and including the first one, you leave that alone. So I just leave that as a 1. But everything after that, you flip the bits. So this becomes a 0, that becomes a 1, that becomes a 0. So the negative of this number in 2's complement form is that. So now I want to add the opposite. So I'm going to add this. I'm going to add the negative. So I'm going to add a 0, 1, 0, 1. So now it's a process of addition. The reason this works, I think it's easier, is because it's really easy to add in binary. So now just remember, that's the 2's complement, which is a negative number. So I got a 0 and a 1. I'm adding now, it's a 1. I got a 0 and a 0. That's a 0. I got a 1 and a 1. That's a 0. Carry 1. I got a 1 and a 1. That's a 0. Carry 1. I got the 0 and the 0 is a 0. And then that carry bit comes down. Well, if you look at this, you say, well, hold on a second, Singleton. Here I got 0, 0, 0, 1. Here I got a 1, 0, 0, 0, 1. But what happens is when you do, this is called 2's complement subtraction. 2's complement subtraction. What you do is you throw away the carry. Throw away the carry bit, and you got the same number. So this is actually an example. Actually, we do the PowerPoint. We'll do the PowerPoint, and I'll go back through this. So it's pretty clear in the PowerPoint, I hope, but typically, when you do subtraction, the fastest and easiest way to do it is to do what they call 2's complement subtraction. Here's an example of it. There's a couple homework problems I give you where you'll practice doing this, so I don't think it'd be a big issue.
Would it maybe be easier to just start with converting the number to a base 10 system?
I can't understand anything you're saying.
Okay.
I don't know if it's my system or yours, but you're muffled. I heard you say, wouldn't it be easier too? I didn't hear anything after that. I didn't mean to cut you off, but I just can't understand what you're saying. Okay, well, let's finish this up, and then if you guys want to talk about something, we can do it. Let's do multiplication. It's really simple. So I got 0. I'm trying to keep it the same order in the PowerPoint as in the PowerPoint. All right, so here's multiplication. And in any number system, of course, a 0 times a 0 is a 0. A 0 times a 1, that's a 0. That's a 0. That's a 1. Now, does anybody recognize, does this look familiar to anybody right here? This is the rules of multiplication. Does that remind you of anything?
Yeah, I guess logically yes, but I don't think we've gone over rules of multiplication since like first grade.
Yeah, so what I was thinking of, remember when we did this? I think we had like a light bulb or something here. We had switch A, B, and X. And we said we can write the truth table for that.
True and false.
Huh?
True, like the and statement.
Yeah, see that? When I add this, I get a 0, 0. I get a 0, 1. So the way they do anything I'm showing you, you have to do with a chip, with logic. So when I multiply binary numbers, all we do is AND them. We just AND them. And I could actually go into the circuitry, the logical circuitry, to show you how to do subtraction, addition, and all that. I won't. This is just kind of just jumps right off, so I thought I would point it out. But keep in mind, we have to do all this electronically, and it's all done with logic circuits. So let me give you these two examples, and I'm running out of time. I want to go through the PowerPoint real quick, and then I'll be happy to answer any questions, and I'll stick around if you have questions. So there's only 2 problems on the multiplication examples, because I still got to go through the PowerPoint. So I got a 1, 1, 1. I want to multiply those. I got a 1, 1, 1, 1. I want to multiply those. So applying the rules to this, I got a 1 times a 1, which is a 1. A 1 times a 1, which is a 1. This right here is a 3. This right here is a 1. So 3 times 1 is a 3. 3 times 1 is a 3 in binary. Pretty simple. This one, you got to be careful, though. You got to do that shifting. You got to shift over to the left. So when I do this, this, of course, is 3 times 3, which is a 9 in our number system. But the way you do it in binary, you got to shift the columns over to the left. I'm looking for a color I didn't use. I guess I used blue. So here I got a 1 times a 1. 1 times 1 is a 1. And 1 times a 1 is a 1. But now when I do this one, I got to shift the answer over. 1 times a 1, I put the 1 not here but here. And 1 times a 1 is a 1. And I'm going to add these. So when I add those, this just comes down as a 1. A 1 and a 1, when I add that, is a 0, carry 1. And the 1 and the 1, again, is a 0, and I just bring down the carry. So if you look at your 8421 code, that's an 8, that's a 1, that's a 9. 9 in decimal, and 9 in binary, I get the same answer. So multiplication is the easiest of all of them, I think. You just do it. Let me go through the PowerPoint quickly, and then I'll do it we went over 90% of it, so I'll do it real fast, and then if you guys got to get out of here, you can, but if somebody needs me to go back over something or you want to talk about something of what I'm doing, I'll be happy to stick around. I don't have another class until 10:30, so I'm good. So let me go through here real quick. There's only 13 slides. Why are we doing this? Well, not so much that you got to do it by hand, but there's a circuit in the microprocessor called the arithmetic logic unit. And so all PLCs, all digital devices pretty much contain that circuitry to do simple mathematics. So I want to look at how that's done with binary numbers, and that's kind of what we walked through. So I showed you already these rules. These are the rules for addition. And then here are the example problems we went over. These are the exact same ones we did on the board. So you can kind of work through those again before you do this. I think there's a homework where you got to do some of this stuff. So just kind of work through these examples again. Make sure you understand what's going on with the actual binary digits. Sometimes you got to carry. Sometimes you got to borrow. These are the rules for subtraction that we went over. And then those are the examples we did. You know, pay attention again to this one right here where you had to actually borrow from here. You had to do some borrowing in here, so I had to change things there. So I think it's hopefully pretty straightforward what I did. But if not, you can ask me about it. And then we looked at 2's complement subtraction. So we did an example, and this is just kind of qualifying it. There's different ways to do it. So I was very specific in my example because we're not going to do a whole lot of this. I just kind of want you to know what's going on in the chip. Did I skip over a slide? Yeah. So this is the actual 2's complement example that we did. Same one. We did it by direct subtraction over here. Then to show you, it's much easier. If you convert this number, you convert that number to a negative by taking the 2's complement of it. Then you get to add it, and it's a lot easier to do. You just throw away the carry bit. So I showed you that. And then rules for multiplication. That's just ANDing. And then we did these 2 problems as an example. So the only thing here is that you got to remember that when you have more than one digit, you got to start to shift that number over. So pretty simple. Now, there's this chip in your microprocessor called an adder. And usually there's just one device. This adder, because if you think about it, we have four four operations that we do. We can add, we can multiply, we can divide, we can subtract. Well, really, multiplication is just a shorthand way of doing division. Multiplication is a shorthand way of adding. Like I can add 3 plus 3 plus 3 plus 3. I can add 3 4 times, or I can just remember that 3 times 4 is 12. When you multiply, it's kind of a shorthand way of adding, and when you divide, it's a shorthand way of subtracting. So we really don't need the multiplication or the division capability in our logic circuit. We can do everything by addition and subtraction. And the fact that these chips, even though it might take a long time for a human to add up numbers, computer can do it really, really quick. So I don't even need the circuitry to do multiplication and division. I can do multiplication in terms of addition, just add the numbers up real fast if I'm a computer. I can do subtraction, a division in terms of subtraction. Well, it turns out since I showed you the 2's complement subtraction, I don't even need the subtraction circuit because I can do addition. I can do subtraction in terms of addition if I can add the negative number, which I can do in the form of a 2's complement process. So the point of this slide is that a lot of digital devices only need an adder. It can do all those 4 operations using this one single chip called an adder. Now, it's a little bit more complicated than what I'm showing you because I have the inputs are 4 bits. You would need way more than that, but the point is it can be done. And I think that is the end of this presentation. So that's it for me, guys. I'm going to, it's 10 o'clock now, so I'm going to, if you need to get out of here, you can. I'll stick around. I don't have another class until 10:30, so if anybody has any questions, I'll be happy to stay here and answer your questions. I see that somebody already sent me 2 questions. Oh, Jacob was saying, wouldn't it be easier to convert to base 10 and then back to base 2? Jacob, yeah, it will be easier. It would be a lot easier to do that. But remember what we're doing. We just want to know what the circuit is doing. We're not doing this because you got to do this by hand. This is the way you're going to calculate numbers. I want you to see what the actual chip is doing with the 1s and 0s. So the whole purpose of this exercise is just to see what the electronics is doing. So we kind of walk through the way the computer thinks. And then Daniel says, oh, okay, you answered that. My guess is you could, but this is, yeah, exactly right, Daniel. That's the point of this. All right, anybody else?
I've got a question on adding. I'm trying one of the problems right now, and it's 111 plus 110.
Wait a minute. That one?
Yep.
All right. You want to do it, or what's your question?
Well, once you get to the end, you're going to have 3 1s that you'll have to add together. So does that mean you just add 2 more places at the end?
So you go a 1 and a 0 is a 1. A 1 and a 1 is a 0, carry 1. And then you'll say, I got a 1 and a 1, that's a 0, carry 1. I got a 0 and a 1, that's a 1. But then you got to take this carry and bring it down. So that's a 1. Okay, so yeah, you're right. I had to move that over. I had to shift it over.
I also just have a question out of curiosity. So Windows,
You're breaking up again. I heard you say you have a question out of curiosity.
Yeah, if Windows, so I guess Windows is 64-bit system. Yeah. So does that mean you can add all the way up to 2 to the 64th power?
Yeah.
That's the maximum value?
Yeah, 64. The 64-bit system means that remember we talked about word size. We said we have a bit is a. I keep looking at my my projector up there. We talked about word size. When they talk about Windows being originally it was 16 bits, and then it went to 32 bits, and now it's 64 bits. What that means is the word size is 64 bits. So remember we said that we have certain fixed sizes, like a bit is just a binary digit, right? A nibble is 4 bits, and a byte is 8 bits. Those are defined. Well, a word is machine dependent. That means that whoever designs a computer, whoever designs a digital system, they can make the word size as big as they want. Now, there's disadvantages to that. The bigger the word size, the more complicated my device is. But the bigger the word size, when I move information around, I don't grab bits. If I have a 64-bit word size, I can grab 64 bits at one time, and I can move it around. But you're exactly right. I'd have to put here for those words, I have to put 64 spaces, and then start doing that 1, 2, 4 to get the value of it. And I think, I don't know if did you ask if the highest, what was your second question?
Yeah, so if it's base 2 with the highest value, I mean, there'd be more, it could be higher than this number, but in the 64th spot, it would be the value of that spot would be 2 to the 64th power.
Yeah, that's exactly right. Yep. And I don't know what that number is, but I'm sure you can put it in your calculator and see. But that's a huge number. But yeah, that's exactly what that would do.
I think that kind of reminds me of when you use like those really crappy calculators in school, and you just keep adding and adding and adding, and then it would give you an error eventually.
Yeah.
Because you're past.
Because when and it's kind of crazy because all we're really doing is moving these bits around. But I think in a lot of those early calculators, and you would get error when you can only address a certain amount of memory. So once you run out of memory, some of the early computers, I think one of the very first computers only had a memory of 256 bits, not bytes, but bits. And so then you go on and went to kilobytes, and so now of course we're at terabytes, and it doubles it more than doubles every 12 to 18 months. There's something called Moore's Law. Moore's Law that talks about how memory doubles about every year to 2 years. So yeah, that's the big limit is how much memory can you address, and then you're moving this stuff around. Remember, we got to move these zeros and ones. You can't do it in a serial fashion. When you deal with a lot of bits, you gotta do a lot of what we call parallel processing, move things around in parallel to keep the speed up. So yeah, it's really, really complicated system. We're actually reaching limits of what we can do with these zeros and ones and the silicon chips. We're reaching limits. So now the next thing was 2 things you might have heard of. It's optical computing, where we use actually photons of light instead of electrical current, and then quantum computing, where we actually can store bits, the presence or absence of a group of atoms, or in some cases individual atoms. Now that's a way above my head. I don't want to go into it. I don't know a lot about it, but it's really interesting the way things are going. But yeah, you're thinking about that the right way.
Cool, thank you.
That's a good question. We got who is that?
I have a question.
Sure.
So for the quiz this Friday, are we supposed to mainly study the stuff from the previous week, like week 2? Because I noticed that for quiz 2 is mainly over the week 1 material. Should we focus on the week 2?
I try to lag behind to give you a chance to make sure everything is done, homework and all that. So yeah, I lag behind a week. That's right. Okay.
I just wanted to make sure.
And who is that? Who am I talking
to? Ben.
Ben, so would you prefer, my original intentions were give the quiz on Friday, right? Give the quiz on Friday. But then, I don't know, I was gonna give it on Friday, that way everybody can take it at the same time. I kind of like that, because I don't think anybody would share answers, but that's something that students could do. But then I think the weekend is kind of laid back, and you can kind of do it any time. What do you feel about that? Doing it on Friday at the same time, or over the weekend anytime you want? But once you start the quiz, it times out. It doesn't matter. It doesn't matter to you.
I can actually add to that. I'm coming back. If you want to answer that question right now, you can. Mine's gonna be like kind of long.
I'm fine with either. We haven't really had a quiz on a Friday yet, so I don't really know what it's like yet compared to taking over the weekend. So,
All right.
For me, I actually talked to a couple of my other professors about this. I'm coming back from like a year-long co-op, and I am moving like all my stuff from Pennsylvania, which is 9 hours away, back here. So
Okay.
like the last 2 weeks, I've just been going like there and back, and have just had like my head up in crap, just trying to deal with all that stuff. So I was gonna ask if I could actually take it before Friday, because I want to leave Thursday afternoon, so I can have the weekend to sort of get the rest of my stuff together, and then come back and like move into my new place.
Okay. But that's just kind of a one-time thing, though, right?
Yeah.
Yeah. Once you do it, okay. All right.
But if I can take it, like, I'd rather not have to deal with doing schoolwork this weekend, or
Right.
so I don't want to have to like forget about it. So if I could take it before Friday.
Yeah. So if I do that, I have to make it available because I can't just set it for one student. I don't think I can do that. I don't know if I can do that. Maybe I'll look into Canvas, because there's a lot about Canvas I don't know yet. So I'll look into it. But if I do that, I don't mind doing it. I can make it available on Thursday, and then you guys, because since we lag behind a week, there's really no reason why you couldn't take it on Thursday. So yeah, I can do that. I can make it available on maybe from Thursday to Saturday or Sunday or something like that.
Okay.
The quiz on Friday works good, because in about 2 weeks we'll go to where we're just meeting once a week, and you guys will do labs the first, on Monday and Wednesdays during this time. You'll do labs at home, so that gives us a reason to meet, get the quiz out the way, and then. But yeah, I'll do that for you. Send me a text. Just send me a text and just remind me.
Okay, I'll send it right now.
I'll make that quiz available tomorrow. You send me a text, and then the Friday thing I'll think about. I don't know. Like you said, we hadn't really had a quiz on Friday. That's the way I did it last summer, and I think students were okay with it. But then I was like, well, maybe they prefer to have it over the weekend. So anyway, anybody have any other questions or comments?
I don't know what UC is doing this semester, but is there a chance that classes will meet in person eventually, or is it just strictly going to be online this semester?
I haven't really heard anything. And this is a rumor. This is a rumor. I don't want to start, but the rumor is that probably in summer we might be meeting face to face again. There's a rumor. So I don't know if that's the case. If I find something out, I don't mind sharing it with you. But right now, I think they're probably looking at summer.
Okay. Yeah, just curious. Didn't know if you knew anything.
Yeah, definitely Hamilton County's in the purple still, but the numbers are going down. And I think when they push that vaccine out, and people do what they're supposed to do as far as masking up and social distancing and all of that, and the numbers start to drop, I don't see any reason why they wouldn't. I think students prefer to be face to face. I know I do. So we'll see what happens.
Yeah, I agree.
So, okay. Anybody else who has been? Hunter was just talking, and Alexander. You haven't said anything. Okay, well, guys, if you're no more questions, I'm going to prepare for my other class. I will see you on Friday. Stay safe. If you have any questions, just send me a text, and I'll be happy to address it. And I'll make that quiz available tomorrow.
Okay, sounds good. Thank you.
All right, everybody, have a good one. You guys.